Welcome to Lesson 3 of 4 in this tutorial, Applications of Hess's Law. This is the third video in our series of 4 lessons on the topic of energetics. In the last lesson, we looked at the equation of energy transfer and used it to calculate the molar enthalpy change for a reaction. Here are the key learning objectives for this session. First, we will look at Hess's law, and then we will look at Hess's law calculations. Here are the AQA specification points for this tutorial. Pause the video now to have a quick read through them before we begin. We'll start off by looking at Hess's law. Hess's law states that the total enthalpy change of a reaction is going to be independent of the route taken. According to Hess's law, the total enthalpy change of a reaction is only dependent on the initial and final states of the reactants and products. It is independent of the path taken to calculate it. You can use Hess's law triangles like this one to carry out calculations for enthalpy changes of experiments in which it is difficult to measure the enthalpy change directly. First of all, we should write down the enthalpy change of the reaction, as you need to calculate the horizontal equation. Next, we should write the symbol delta H near the arrow, as this is the unknown enthalpy change you want to calculate. Then, we can put in the other bits of information we know in order to make a triangle. The other bits of information will consist of the enthalpy changes of formation or combustion of either of the reactants or the products. After this, we can write down the known enthalpy changes of the reactions that are known over the arrows of the equations by looking at the values provided in the question. These are shown here. Finally, we can find the easiest route around the diagram, which will enable us to find the unknown enthalpy change. So for here, we would do x plus y is equal to delta H. Here's a quick summary of what we've just covered. Pause the video now to take a quick note of this. It will come in handy for your revision. Hess's law can be used to calculate the delta H of a reaction that cannot be measured directly from an experiment. Now, we'll be looking at performing calculations with Hess's law, including the calculation of enthalpy changes from reactions. To calculate an enthalpy change, we need to use the enthalpy changes of formation of the reactants and products. If we have the reaction A goes to B, we can form a Hess's triangle. Both the reactants and products involve the exact same elements, so they are formed from the same elements. Therefore, we can write these elements across the bottom, shown here as the letter C, and calculate the enthalpy of formation of the reactants, which is A, and the products, which is B. To calculate the enthalpy change of reaction from the enthalpy changes of formation, we can use the following 3 equations. First, we'll look at the enthalpy changes of formation of the reactants and those of the products. Then, we can calculate the unknown enthalpy change of the reaction. First, we need to draw a Hess's triangle. Next, we need to find the key enthalpy values given in the data table. And then we can calculate the enthalpy change of the reaction. We can do this by using the enthalpy of formation of the products and the reactants. If an element is in its standard state, its enthalpy of formation will be 0. Let's try this practice question. Pause the video now to have a go at it by yourself. This is the answer. Let's go through it step by step to see how we got there. First of all, we need to draw the Hess's Law triangle. So in this instance, we're going from Li2CO3, which is a solid, into Li2O, which is also a solid, and CO2 gas. To draw a triangle, we need to go from the reactants, which would be 2Li, and carbon, plus 1.5 O2. We can get to here through route 1 or route 2. Now, we need to find the key enthalpy values. These have been given to us in the question, which is shown here. The bottom has all of the elements that are needed to form each of the reactants and products. Normally, the enthalpy values will be given to you in a data booklet, but you will need to work out which value to look up. The enthalpy changes of formation only occur when 1 mole of the substance is made. Let's move on to step 3. Now we need to calculate the enthalpy change of the reaction. So we can do route 1 is equal to route 2. We don't know what route 1 is, so we'll leave that as delta H. Route 2, however, we can calculate. This is going to be the delta H of the reactants and the products. We have to put a minus sign in front of the reactants in this example. If we go the opposite way on the arrows, then we have to reverse the sign of the enthalpy change. Remember, the enthalpy of formation for an element is 0, since no energy would be required to convert an element into an element. If we have the reaction A goes to B, we can form a Hess's triangle. Using this triangle, again we can calculate the enthalpy of combustion of A and B. In this triangle, CO2 and H2O are always at the bottom. This means that the enthalpy change of combustion can only be used for organic equations. Both the combustion of the reactants and the products will be CO2 and H2O, as shown here. To calculate the enthalpy change of the reaction from the enthalpy changes of formation, you must use the following 3 equations. The enthalpy changes of combustion of the reactants and the products, and the unknown enthalpy of the reaction. First, we need to draw a Hess's triangle. Then, we can find the key enthalpy values from the data table and calculate the enthalpy change of the reaction. We can do this by using the enthalpy change of combustion of the reactants and that of the products. Let's try this practice question together. Pause the video now to work it out by yourself. Here's the answer. Let's go through it together. First of all, we need to draw Hess's triangle. So in this instance, we're going from 3C solid plus 4H2 gas into C3H8 gas. We know that down here we have to write CO2 and H2O. So we've got 4 H2Os and 3 CO2s. We can get to this via root 1 or root 2. Next, we can find the key enthalpy values. These are given to us again in the question here. Now we can calculate the enthalpy change of the reaction. So once again, we would do root 1 is going to be equal to root 2. We don't know what root 1 is, so we say that equals delta H. However, root 2 is going to be equal to the combustion of the reactants and the combustion of the products. Now we can go through step 2. This leaves us with the answer minus 2326. Since we are calculating the enthalpy change of combustion of the products, we need to reverse the sign and calculate root 1. If we have more than one mole that is being combusted, we need to multiply the enthalpy change of combustion by the total number of moles of compound that is present. This is usual in AQA exams for questions with higher amount of marks. We have now covered both the learning objectives for this session. Feel free to pause the video now and re-watch anything you're unsure about. We have now completed Lesson 3.